So Hongye is an incoming HQA fellow at Harvard, starting in the fall of 22. And currently he's working as a consultant for Q-era computing. He did his PhD from UCSD like 2 months ago, where he worked on classical shadow tomography. He also did as an intern at the NASA quantum AI team, where he worked on this paper called logical shadow tomography, using which you can do efficient estimation of error mitigated observables. And today he's going to be talking about that. So Hongye, please go ahead and take it.
Okay, thank you for the very nice introduction. So good morning, everyone. My name is Hongye. I'm an incoming postdoc fellow at Harvard. So I would like to thank the organizer for giving me this chance to talk about our recent works. So today, the main focus is on logical shadow tomography, which is an efficient error mitigation method we proposed recently. And in the end of my talk, I'll also cover a bit on how to do shadow tomography with the near-term quantum devices. So the first work is in collaboration with Ryan, Yizhuang, Eleanor, and Zhihui, and the second work is in collaboration with Yizhuang and Songwen Cui. So over the past few years, we have witnessed great progress made in quantum computation. Scientists from both academia and the industry have proposed several prototypes of a quantum computer based on, for example, superconducting circuits, trapped ion system, neutral atoms, and also quantum optics. So quantum computers can be viewed as a machine that utilize the quantum gates to prepare a quantum state. However, those bare physical qubits inevitably will have noises resulting from noise in environment. So due to the noise, we can only run really short circuits. And it also has been shown that if the noise surpasses the threshold, there is no visible quantum advantage. However, on the other hand, in the long term, scientists also have shown that quantum computation can be performed infinitely with the help of quantum error correction code. So in the fault tolerance regime, there are certified quantum advantages. For example, the famous Shor's algorithm. However, it's still very challenging to enter this fault tolerance regime because it requires many qubits to encode logic qubits, and it also requires fast syndrome readout and decoding. So those put a very stringent requirement on the hardwares. So in the transition from these bare physical qubits to the fault tolerance regime, we are interested in quantum error mitigation methods that are hardware friendly. And hopefully with error mitigation, we can run the quantum circuits in a moderate amount of depth. Another interesting question is whether there are any useful quantum advantages with shadow circuits. So in today's talk, I'll first introduce what is quantum error mitigation and review some existing quantum error mitigation methods and their pros and cons. Then I will give you a short introduction on the classic shadow representation, which is originally proposed by Robert, the first speaker. So with those backgrounds, I will introduce the logical shadow tomography and its properties. And in the conclusion and outlook part, I'll also briefly mention the current exciting progress made on the classical shadow tomography beyond the group structure. So first, let me define what is the quantum error mitigation. So an ideal quantum computer can be viewed as a machine that utilizes the perfect quantum gates to prepare a quantum state phi. And usually the solution we are interested in is encoded as some linear property of the final quantum state. However, those real devices inevitably will have noise, and those gates are not perfect. Then the final state will also become noisy. Therefore, the linear property O will deviate from the ideal expectation value. And on a high level, the quantum error mitigation aims to get a closer prediction on those linear properties with respect to the ideal expectation value compared to those bare implementations. And quantum error mitigation can be performed either on a real device, such as a dynamic decoupling, or in some data post-processing phase. So for example, the quantum error mitigation methods on the bare physical qubits, including the dynamic decoupling, quasi-probability expansion, noise, zero noise extrapolation, and etc. And also more recently, the quantum error mitigation method beyond the bare physical qubits encoding are proposed. For example, in the subspace expansion, it mitigates the errors on error correction code embedding, and virtual distillation use coherent copies of the physical system to mitigate errors. And in the following of my talk, I'll mainly focus on the last two methods and introduce their pros and cons. So first, let's take a look at the error mitigation with a subspace expansion. So it can be viewed as a quantum error mitigation method with a quantum error correction code, but doesn't use any active quantum error correction. So in order to protect the valuable logical information, people distribute this logical information to many physical qubits. So the stabilizer error correction code is usually defined by this stabilizer group. For example, in this 513 code, stabilizer code example, people use 5 qubits to encode 1 logical qubits. And the stabilizer group is specified by those 4 polystring generators. Therefore, in total, the stabilizer group will contain 2 to the 4, which is 16 group elements. Then the logical subspace is the eigenvalue 1 subspace of all the group elements. And also the logical X and Z operators will be some non-local polystring operators. For example, the 5X and 5Z in this 513 code example. So if there is any local error happened, it will actually perturb this logical state out of the logical subspace. But any local error won't corrupt the logical information. Therefore, if we can project the final noisy state back to this logical subspace, we can effectively get rid of those non-logical errors. And the projector associated with the stabilizer code can be written as a product of all these stabilizer generators plus 1. And if we expand this product, we see the projector can be written as a summation of all the group elements inside the stabilizer group. So in the subspace expansion, people propose that we can first project this noisy final state to the logical subspace to get rid of these non-logical errors, and then get a linear readout O. However, this projection is not easy in the experiments. So how do we achieve that? So in order to achieve this, people propose that we can expand this projection operator into all the group elements. And in the experiments, we can measure this linear property, and effectively, when we do the summation will achieve the projection to the logical subspace. So this is nice in a sense that we can actually run this experiment in the near-term quantum devices, just a linear readout. However, the caveat is that in order to expand this projector, we see that we have a huge summation that sum over all the group elements, and that is going to scale exponentially with a total number of physical qubits. So suppose one have 20 physical qubits to protect the 1 logical qubits. There are already 1 million group elements in the stabilizer group. So this summation is not really scalable. And in the error mitigation with virtual distillation, people propose to first raise the rho epsilon to the nth power and then get a linear property O. So suppose rho epsilon is a given state with temperature T. This method will give us an effective property of a lower temperature state with temperature equals to T over M. And the rho to the mth power is effectively achieved in experiments by preparing M coherent copies of the quantum states and doing this swap measurement. So as we see, the subspace expansion and virtual distillation are great error mitigation methods, which do not make strong assumptions on the noise model. But inevitably, they require many quantum resources. For example, in the subspace expansion, we need many measurements. And in the virtual distillation, we need coherent copies. And we want to ask the question whether it is possible to achieve the same error mitigation capacity as the subspace expansion and virtual distillation, but with less quantum resources. For example, less measurements, less or no coherent copies. And luckily, the answer is yes. So it can be achieved by utilizing the randomized measurement. So the key observation from the recent development of randomized measurement is that any quantum state can be represented as a linear combination of the stabilizer state. And the projection to the logical subspace can be efficiently carried out on a stabilizer state without expanding the projection operator. Now let me give a short introduction on the classical shadow representation. So it can be viewed as a general framework of the randomized Pauli measurement. So in the classical shadow tomography, we have an ensemble of unitary transformations. So each time in the experiments, we sample a unitary from this ensemble to evolve the quantum state, and rho will be mapped to rho prime. And then we take a computational z-basis measurement. So the rho prime will collapse to a B-string state. I'll use cat B to denote it. Then on a classical computer, we calculate the back evolution of the cat B state with the corresponding unitary we use in experiments to get this sigma hat. And this sigma hat is what people call classical shadows. So equivalently, we can think we're doing some complicated projective measurement directly on this original, on this underlying state. But this projective measurement is the back evolution of the computational z-basis measurement. And after this projective measurement, this quantum state will collapse to the classical shadow sigma hat. So when this unitary ensemble consists of global Clifford transformation, so each of the U is a Clifford gate, and the cat B is a B string. So we see the sigma hat is effectively a stabilizer state. And then with many experiments, we have a set of the stabilizer state and the distribution of the stabilizer state depending on the underlying quantum state rho. So it can be shown that the underlying state rho is just a linear combination of all these classical shadows. So from this, we see a generic quantum state can be represented as a linear combination of the stabilizer state. And this stabilizer set can be got from the experiments. So since the projection by a stabilizer group on a stabilizer state can be efficiently calculated on a classical computer, if we have the classical shadow representation of this final noisy quantum state, we can efficiently project it to the logical subspace without expanding the projection operator. And this can be carried out on the data post-processing phase. And also the nonlinear properties such as rho to the kth power can be also calculated. Also as a tomography scheme, this also have a really nice provable efficiency when we use the global Clifford transformation. So the key observation is that both subspace expansion and virtual distillation can be efficiently evaluated with the classical shadow representation in the data post-processing phase. So with this intuition, let me introduce the logical shadow tomography. So in logical shadow tomography, we still use error correction code to distribute this logical information to multiple physical qubits. And in this cartoon, each of the red dot is a logic qubits, and each of the blue dots are physical qubits. And then once we do this encoding, we can perform the quantum computation without the active quantum error correction. And also for any stabilizer code we are using, there is a projection operator associated with the code. And since there are some errors happened on each of the physical qubits during this quantum computation, the final state will become noisy, so it will become rho epsilon. So the way we mitigate errors is that after quantum computation, we want to get the classical shadow representation of this final state rho epsilon. So we apply a global Clifford transformation on each of the logical qubit sector and perform the computational basis measurement. So for each measurement results, we will have a stabilizer state as our classical shadow. And with some measurements, we have a set of stabilizer state. And they are the classical shadow representation of this epsilon, rho epsilon. So on the classical computer, then we can efficiently project this row back to the logical subspace and predict the error mitigated linear property O. And moreover, we can use the same data to raise the row to the mth power and achieve the effect of virtual distillation without the need of many copies. So by utilizing the randomized measurement, it seems we can predict many properties of the error mitigated property of the row. So one may ask, what is the sample complexity compared to the subspace expansion? So in subspace expansion, if we want to measure error mitigated properties OI, the number of measurements will scale linearly with M. And for each of the OI, we need to expand this code projector P to exponentially many polystrings and measure them one by one. So in total, the number of measurement will scale as M times e to the total number of physical qubits. But for the logical shadow tomography, with the power of cosmic shadow, in the paper we proved the sample complexity will scale as log M times e to the number of logical qubits. So in this cartoon, the number of physical qubits are 10, while the number of logical qubits are just 2. So in practice, as you can imagine, that is a great reduction in the sample complexity. In addition, in the paper, we also show the error will be suppressed exponentially with respect to the code distance of our error correction code we are using. So suppose one qubit, the fidelity of 1 qubit is 90% under some stochastic error. Then with a 513 code encoding, the fidelity of the logical qubits will boost it to 99.9%. So first, let's revisit the 513 code example, which is also used in the subspace expansion, where each of just one logical qubit is encoded with 5 physical qubits. The stabilizer group is generated by those 4 polystrings, and in total there are 16 group elements. So suppose this logical qubit is in an arbitrary quantum state, and each of the physical qubit is subjected to some depolarizing noise. We use the infidelity to measure how good the error mitigation is. So if this infidelity is 0, it means there is no error. And in this figure, all these dashed line are the theoretical results, and the solid line are the practical results from the sampling. So let's first take a look at the theoretical results. If one do not use any quantum error correction code embedding and the physical qubit is subjected to depolarizing noise, then this black line, dashed line, indicates the infidelity of this qubit with respect to different error rates. So as we expected, the infidelity will increase linearly with P. However, with the logical shadow tomography with M equals to 1, we have this dashed line. In the small p region, the infidelity will scale as p to the third power. And as we see, if the error rate is smaller than 50%, it is always beneficial to use the error correction code embedding. And people also call this 0.5 the pseudo threshold. And the logical shadow tomography with rho squared can be also calculated, and is indicated by this blue line. So in the small p region, this infidelity will scale as p to the 6th power. And as we see, of course, it will have a higher threshold. So having understood these theoretical results, let's take a look at how their practical performance with a finite amount of measurements. So as a fair comparison, we use 150 measurements for each of the methods. So those solid lines indicates the mean value, and these shady areas indicates the first standard deviation. So for the subspace expansion, we see even though the red line agrees well with the theoretical results, however, this red shady area indicated the prediction will have a really huge statistical fluctuation. That is because we have 16 group elements in the numerator, and also in the expansion, we have 16 poly we need to measure for the denominator. So each of the poly is measured less than 100 times. That's why you have a huge fluctuation. Well, if we use the logical shadow tomography with same amount of measurement, the glue this green shady area, as we can see, is dramatically reduced. And in addition, with the same amount of data, we can also estimate logical shadow tomography with rho squared. And this is indicated by this blue line. So since we only have one copy of the system, the traditional virtual distillation cannot be applied. So this is a really small system where the subspace expansion can be applied. So suppose we have multiple logical qubits, then the number of group elements in the stabilized group will be enormous, and the direct methods will fail. So now let's take a look at the multiple logical qubit cases. So we consider a multi-logical qubit J-state preparation. So each of the logical qubits is encoded with n physical qubits, and we assume each of the physical qubits is subjected to 1% depolarizing error. So in this left figure, we estimate the logical XX operator for 2 logical qubits J-state. In the ideal state, the expectation value will be 1. And each of the logic qubits is encoded with n physical qubits up to 20. So different color means different number of samples. So for example, if we use 20 qubits to encode 1 logic qubits, then there are roughly 300 billion group elements in the stabilized group. And it is really infeasible to use the traditional method and expand this projection operator. However, with logical shadow tomography, we see that with 20,000 samples, this orange dot already gave us a really good estimation, and moreover, the error bar is really small. In addition, when we look at the error bar, we see the error bar actually doesn't grow if we increase the number of physical qubits in this embedding. And this error bar indicates the sample complexity of the method. So when we plot it, we see in practice, the sample complexity, it doesn't show strong increase when we increase the number of physical qubits, which is really nice. In addition, we also tested the sample complexity scaling with respect to the number of logical qubits. So here we encode 1 logic qubits with 5 physical qubits, and we increase the number of logic qubits. And as we see, indeed, the error bar or the standard deviation will increase as we increase the number of logical qubits as we expected. And in practice, it scales as 2 to the 1.1K, and K is the number of logic qubits. So here, the scaling is still in favor to the full quantum state tomography, and we want to emphasize each of the logic qubits is also encoded with 5 physical qubits. So it's a much larger system. So with this test, we see practically the sample complexity agree with our understanding. And as a summary in this work, we introduced the logical shadow tomography, which uses classical shadow representation, naturally combines subspace expansion and virtual distillation. And we have shown the error will be suppressed exponentially with respect to the code distance of the error correction code. So last but not least, we have proved the sample complexity only scale with the number of logic qubits, which is an exponential reduction compared to the subspace expansion, and there is no need for coherent copies to achieve the virtual distillation. So the only extra part we introduced to achieve this logical shadow tomography is to achieve a global Clifford transformation for each of the logical qubit sector. And for those who are familiar with the experiment, it is known that it will use relatively deep circuits to achieve this global 2 design. So one may ask, if we want to use the shallow circuit, could we still do the classical shadow tomography? The main challenge of doing the classical shadow tomography with shallow circuit is that the reconstruction map is previously unknown. And luckily, with the current development, we have found the reconstruction map in our recent paper, where we introduced this locally scrambled shadow tomography. So here I'll briefly mention its results. The locally scrambled shadow tomography can be viewed as a general framework of classical shadow tomography. And the biggest advantage of this locally scrambled shadow tomography is flexibility in the circuit ensemble design. So previously, we required the unitary ensemble to form a group, but here in the locally scrambled shadow tomography, we don't need to require a group. So since the flexibility, we can use a various choice of quantum circuits for the near-term quantum machines. Some example including the shadow random circuits, fixed unitary circuits with unsteady random gates, some chaotic dynamics. So here I just want to show you two examples where the classic shadow tomography is impossible previously. One is a locally scrambled signal circuit, and the other one is a locally scrambled Rydberg dynamics by a fixed Hamiltonian. So in our preliminary results here, we have shown the sample complexity of those two examples already achieve approximate optimal bound. So in this figure, we plot the fidelity of the reconstructed J state as a function of a number of qubits, and different color means different scheme. So the blue line indicates the randomized Pauli measurement, and the red one is a locally scrambled signal circuit. The green one is a locally scrambled Rydberg dynamics. And in the inside, this line indicates the sample complexity. So as we see, if we use randomized Pauli measurement, the sample complexity will grow exponentially if we increase the system size. However, with either the locally scrambled CNOT gate or the locally scrambled Rydberg dynamics, we see the sample complexity almost doesn't grow with the number of qubits. So this really speaks for the advantage of locally scrambled shadow tomography and is ready for the near-term quantum machine. So to conclude my talk, I think combined with the progress of locally shadow tomography, this new quantum error mitigation technique is ready for the near-term quantum devices, and we hope to test it in the future with either analog-based or quantum circuit-based quantum computers. And with this, I'll conclude my talk, and thank you for your attention.
Thank you again for your talk.
Yeah, thank you.
And so if anyone in the audience have any questions, feel free to unmute yourselves or put it in the chat and you please talk.
I have a question. I was wondering what's the advantage of using quantum error correction over the quantum error detection codes for the subspace expansion or the logical shadow tomography?
Oh, I see. Yeah, thanks for the great question. So in terms of to do this active quantum error correction, you not only need to do this encoding, but you also require to do the syndrome detection, which to achieve that, you need other ancilla qubits to do this detection without destroying this quantum state. And with that syndrome detection, you also need a really fast syndrome decoding to do the active quantum correction. So in together, in order to achieve this active quantum action, it really needs more qubits than the subspace expansion, but it also requires really fast syndrome detection and decoding. So that is really hard. So I think as a first step, maybe people can test just to do this encoding and do this error mitigation instead of doing the active syndrome detection, which is much harder.
Yeah, but you're not actively correcting the errors. So is there any advantage of using error detection codes in the shadow tomography? Because you're reducing the physical qubits, or for the subspace expansion, it was exponentially increasing the number of measured the physical qubits. So would that be an advantage? Not in your work, because it scales with the number of logical qubits, but there could be an advantage. But I'm wondering have you considered this using error detection codes in this shadow tomography?
Mm-hmm. I see. Yeah. So indeed, if we use the subspace expansion, that is not favorable because we need to do many measurements. And here, even though we reduce the sample complexity, it still scale with a number of logic qubits. But I think it is possible to further reduce the sample complexity by using proper design of the extra gate to achieve the shadow tomography, but also that puts requirement on like how could we perform the shadow tomography. I think, but we haven't. Yeah, so the main idea is that we don't want to actively detect the error, even though this method will not scale to a really deep circuit. If the error happens very frequently, with a larger chance, the logical error will happen. So the assumption is that we still want to run shallow computation, but it's relatively deep compared to the Barry implementation. I hope that answers your question.
Yeah, good. Thanks.
Good. I think this is probably a good time